Thank you for the introduction. Good morning, everyone. My name is Alejandro. I'm a PhD candidate in the Mechanical Engineering Department studying electrochemistry. And our project is Halogen. We're creating a battery, a non-rechargeable battery with the highest energy density in the market. Primary batteries are non-rechargeable devices that can be found everywhere. They're in this room inside critical safety devices such as fire alarms and other sensors. They're in your pocket if you have a smart tag or your car keys. If you drove here, they're inside your car tire pressure monitors, your E-ZPass, and in many other places. These batteries are used because they can last a really long time. Their energy density, or how much energy you can pack inside them, can reach over 3 times greater than rechargeable lithium-ion batteries. This makes them really critical, especially in applications where recharging is impractical or not needed, such as in medical implants, sensors for Internet of Things, and defense-related applications. Across these applications, high energy density is very important. Why, do you ask? Well, let's take a look at cardiac pacemakers as an example. These are basic life support devices in which the battery only lasts between 5 to 10 years. After the primary battery inside them has died, the whole device needs to be replaced in a surgery that is both costly and complicated. If you want these batteries to last longer, you need to pack in more energy in there. We conducted over 100 interviews, and what we learned was that medical device manufacturers are eager to add more therapies into their devices, requiring more power and energy. Defense agencies are looking to reduce the weight of the batteries that their soldiers or drones carry in order to extend their range, all of which requires more energy per unit weight. I hope that I've convinced you that there's a strong need for high-energy primaries. Despite this, there hasn't been any major cell innovation in cell chemistry in over the past 40 years. This is the challenge that we wanted to tackle and the opportunity that lies ahead of us. Thanks to advancements in organic synthesis, we have developed a new type of primary battery based on the use of a liquid fluorinated reactant, or LFR, as we like to call it. Let's take a look at the traditional CFX battery here, which is the industry leader on the left. In this battery, there's a solid cathode right there in the middle, and that's where all the energy is stored. And it is surrounded by a liquid electrolyte. Every battery needs an electrolyte to conduct ions. However, traditionally, it does not store any energy, so it is just dead weight. Instead, the LFR is an energy-dense liquid. That means that it can store energy in a liquid state, and it can conduct ions, as well as in a liquid electrolyte. This combination of a liquid cathode and a liquid electrolyte is what we call a catholyte. And this 2-in-1 solution allows us to pack in more energy in the same space, achieving greater energy densities. Our team has over 6+ years of experience in fluorinated battery chemistries. This work that I showed you is the result of several generations of iterative design for which we have already filed utility patent applications for, have been published in scientific journals, and featured in some news articles as well. Using only the equipment that we have available to us in lab, we have achieved a 30% energy improvement over the industry leader. Our projections, however, show that over 50% improvement over the state-of-the-art is possible with further optimization on cell-level architecture. And that's what we're hoping to achieve next. If we are successful in achieving this 50% energy improvement, we'd have an impact across different industries. For example, we'd be able to extend the life of medical devices such as pacemakers from 10 to 15 years, improving the quality of life of the patient. We'd be able to reduce the weight of the batteries that soldiers carry on their missions from 20 to 13 pounds and enhance their flexibility throughout their mission. We'd be able to reduce the overall waste from this industry by close to 30%, as fewer device replacements are needed because the batteries last longer. Our technology, importantly, is compatible with existing cell manufacturing line, in which the only key modifications would occur would be the LFR synthesis step and the liquid injection of the catholyte. Importantly, after scaling, our projected costs would be on par with the state-of-the-art. This is because the only key modification and change would be the LFR itself. But the LFR is already produced at scale for pharmaceutical applications. So there'd be no added cost for these additional benefits that I've described. We will continue to scale up our cell technology, specifically targeting performance parameters that will be specific to the beachhead market that we decide on. This will allow us to formalize a business plan and spin out in the near future. Our team is composed of myself, Dr. Haining Gao, a material scientist by training, and our advisor, Professor Beitar Gallant. We're thankful to count on the support of the Deshpande Center and NSF I-Corps. We're looking for advisors who can help us fine-tune this business plan and learn about the mechanics of actually spinning out step by step. We're looking for partners who can help us introduce to cell manufacturing facilities so that can help take our cell to the next level. And overall, we're just looking for people eager to join us in developing new chemistries for established and developing markets. Thank you for your time.